Okay, so now let's take a look at the simulation I've created. First of all, let me motivate this. The analysis we just did was fine, but it only applied to an intensity or signals which are continuously varying. But we know the signals from our detectors are not like that. No matter whether light is quantized or classical, the output of the detectors definitely consists of a set of pulses. It's definitely quantized. So this isn't a contradiction. Again, we might imagine that the way the detectors work is that the probability of getting a pulse in any interval of time is just proportional to the intensity. Okay? So that the probability is proportional to the intensity. But whether we actually get a pulse or not is a random process that's controlled by that probability. So this simulation allows us to test out for that case whether our results from before still hold. Okay? So there are three graphs here, and they're going to show the following. The first is going to show the transmit detector signal. The second is going to show the reflect detector signal. And then the third is going to show the product of these, which is the same thing as showing the coincidences, because only when we have both a pulse from the detector, the reflect detector, and transmit detector will we see a coincidence, a pulse in the product. Okay. And then we can look at three different cases. Let me go ahead and start this. There we go. So in this case, the average intensity is constant, corresponding to a probability of receiving a pulse in any unit of time of 35%. Okay? And but otherwise, the outputs of the two detectors are uncorrelated, as we'd expect for the classical case that we're talking about, because the intensities are the same. So they randomly produce pulses with a probability corresponding to this intensity. Okay? Over here, there are some numbers. These are the number of counts in each channel, the number of pulses from the first detector, number of pulses received from the second detector, number of coincidence pulses. And over here are the average intensities that come from those numbers. And then finally, here's a calculation of G2. Of course, since this is a simulation, the result fluctuates, but you can see that the value is very close to 1. Okay? If we stop this and start it again, you'll see that it might start far from 1, but it will rapidly average towards 1. Okay? There we go. I'll speed it up a little so we get closer faster. There we are. Okay, so this simulation shows that that even when the signal consists of pulses, which are randomly created with a probability controlled by the intensity, our former result still holds. This is shown rigorously and mathematically in the paper by Beck in the references, but I thought it would be nice to look at the simulation because it's sort of more immediate. Now we talked about a second case as well, a case where the intensity fluctuates like cosine squared of omega t. Now that's the next case we'll take a look at. Let's go ahead. Now you can see that the probability of getting a pulse varies with time, but the probability of getting a pulse from the transmit detector and the receive detector both vary with time in the same way. The idea is that the underlying intensity of light is varying in the same way for both. It's varying like cosine of omega t squared. And that's what's shown. That's the white line that's shown here. Okay? All right. Well, the simulation's been running for a little while, and you can see that G2 has approached a nearly constant result. It's not 1 now, it's 1.5. So again, although we see fluctuations, this supports the idea that the analytic result we wrote down a moment ago still holds when the detectors randomly produce pulses with a probability that's determined by the intensity. And the intensity would be a classical continuously variable number. Okay, I'm going to stop the simulation now and we'll go to the third one. So the third case I want to show you is the case where the pulses are anti-correlated. That means that when we get a pulse on the transmit detector, we're guaranteed not to get a pulse on the receive detector and vice versa. And of course, we can guess what the answer will be, but it's still fun to run the simulation. So let's go ahead. So notice if we look at either of these streams, the green one or the red one, they look completely random, okay? But they're anti-correlated, meaning that we never get a pulse from both detectors in the same interval of time, okay? Even though the average number of pulses in any unit of time is the same. And of course, what that means is that the product of the signals is always zero. And so G2 is always zero in this case. So this is what we expect in the quantum case, okay? And notice how different the result is. Let's stop there. Okay, very good. I'm going to stop sharing and stop this video.